Hey everybody, Dr. A here, and in this video we're going to be exploring another example of a statically indeterminate beam. So given to us, we're being asked to compute the external support reactions and then draw the shear and moment diagrams for this beam, and we're being told that the flexural rigidity, which is EI, is constant. So the beam we're given is called a propped cantilever beam. It's fixed at A and it is supported by a roller at B. It's supporting a 30 PLF uniformly distributed load over its entire span, which is 10 feet. So let's go ahead and get started. We're going to start by writing solution. And the first thing we're going to do is we're going to draw the real system, okay? And when we draw this real system, we're going to be able to clearly see just how and why this system is statically indeterminate. So I'm going to go ahead and draw it as a free body diagram. So we have the applied load here. That's the 30 PLF. And then at the left support, we're going to see that we develop an AY, an AX, and a reaction MA. And then at the roller at point B, we're going to develop a BY. And we're going to go ahead and draw the entire dimension line here as 10 feet. Okay, so looking at this, we clearly have 4 external support reactions, so R equals 4. We have one member or one part, so N equals 1. And then we're going to say that the degree of indeterminacy is R minus 3N, which is just 1 degree. So this is statically indeterminate to the first degree. And what we're going to have to do is select one of these external support reactions to be our redundant. So I'm going to go ahead and select BY as the redundant so I can easily apply some deflection equations to my primary system and my redundant system that I'm going to draw in just a minute. So let's go ahead and write that down. We're going to say select BY as the redundant. And you need to remember the selection of the redundant is you have some options here. You don't always have to select one particular reaction as the redundant, but you have to select your redundant such that your primary system will be both statically determinate and stable. So that's the general rule. Now, the follow-up to that is if you select a particular reaction to be a redundant, you want to make that selection such that you can perform some deflection calculations with more ease and have less tedious deflection calculations. So that's also why we're selecting BY as the redundant. So we're going to go ahead and we're going to draw the primary system, okay? And when we draw the primary system, it's going to look similar to the real system. It's going to have the real loads acting on it, so that 30 PLF is still going to appear here. But instead of having BY, we're going to remove BY's effect completely. So we're going to have the fixed connection at A, but BY is removed from the figure. And we still have the total length of 10 feet. Now, when we remove BY, we're going to allow this primary system or the primary beam to deflect. And you're going to have a nonlinear deflection diagram the whole way through. This is nonlinear. And you're going to develop a deflection at point B called delta sub B. And we can use a ready-made pre-derived formula to calculate delta sub B, and you can find this formula in pretty much any mechanics of materials or structural analysis book. That's going to be WL to the 4th over 8EI. Okay, now we're going to go ahead and substitute values in. That's going to be 30 PLF times 10 feet to the 4th power over 8 EI. And if you punch this into your calculator, you get 37,500 pound-feet cubed, all divided by EI. So the EI stays there for now. You have to continue to include the EI in that denominator. Now we're going to draw the redundant system. So that was the primary system. Next, we're going to draw the redundant, I'm going to abbreviate that, redund system. Now, a redundant system geometrically is going to look very similar to the primary system. It's going to be a cantilever beam that's still fixed at A. But now we're not going to include the real loads here. We're only going to include BY, and we're going to treat BY like it's an applied load on this particular system. And the span length is still 10 feet. And so once we apply BY as a load at the free end, we're going to get a nonlinear deflection diagram that's deflecting upward, and we're going to call this delta prime BB. And we also have a ready-made deflection formula for delta prime BB. Delta prime BB is going to be equal to PL cubed over 3EI. Now, what we call P in our deflection equation here is going to be BY. That's going to be the applied load at that free end. So we're going to write this as BY, and then L is 10 feet, so you're going to have 10 feet cubed over 3EI, and we'll end up getting 333.3 feet cubed times BY in that numerator, all divided by EI. Now we got to be careful here, okay? In our redundant system, we see that this delta prime BB is deflecting upwards, and then if we scroll back to our primary system, we see that that delta B, which is coming from this nonlinear deflection diagram, is deflecting downwards. So one of them is deflecting down while the other is deflecting up, and so we have to account for this when we draw or when we write out our compatibility equation. So that's what I'm going to do next. I'm going to say my compatibility equation is going to be defined when things pointing up are positive, and that's going to give me negative delta B, because that was deflecting downwards, plus delta prime BB equals 0. So I'm going to write these expressions in here: negative 37,500 pound-feet cubed over EI plus 333.3 feet cubed times BY all over EI equals 0. And the EIs are going to cancel, because when you add these two expressions together and you set them equal to 0, the EI is common to both terms, so it'll cancel out. We'll see some other things cancel out here as well, so we'll end up calculating BY as 112.5 pounds, and that's going to be a positive number, which means it's reacting upwards, which is the direction we assumed in the redundant system. Now, we're not quite done yet. Now we just need to apply some basic concepts from statics and basic equilibrium to solve for the remaining reactions, and then draw the shear and moment diagram. So I'm going to go ahead and redraw the real system. And in this real system, I am going to sketch on here BY and the applied loads. So we're going to sketch this real system, and we're going to see that it has 30 PLF acting across its span. And then at the left support, we know we have an AY, we have an AX, and we have an M sub A there. And then at point B, we have BY that we just calculated. That's the 112.5 pounds going up. And we still need to draw this dimension line on here. That's going to be 10 feet. So now, if you notice, since we have BY, we only have these three remaining unknown reactions that we can easily solve for. Clearly, we can say sum of the forces in the x direction equals 0, so AX is going to be 0. Next, we can say sum of the forces in the y direction equals 0, taking things pointing up as positive. So we can say AY minus 30 PLF times 10 feet plus 112.5 pounds equals 0. And doing some rearranging here, we'll get AY equals 187.5 pounds reacting upwards. And finally, we can get the moment reaction by saying sum of the moments about point A equals 0. Counterclockwise is positive. And I'm going to say MA minus 30 PLF times 10 feet times 5 feet plus 112.5 pounds times 10 feet equals 0. Solving for the moment reaction at A, I get 375 pound-feet, and that's going to be reacting in a counterclockwise fashion. So these are my external reactions. Now I can go ahead and sketch the shear and moment diagrams. So if you're a little rusty on shear moment diagrams, you need to go back and review these concepts. I am going to go a little bit fast in sketching these. So here, draw that a little bit better for us. We're going to have our shear axis in pounds. And there's our x-axis in feet. So moving from left to right, we encounter AY first, which is going to push us up to the value of 187.5, and then we're going to encounter the uniformly distributed load, which is going to give us a linear shear diagram, and that will push us down to the value of negative 112.5 pounds at the 10-foot mark. And again, this is going to be a linear relationship, so we're going to have a straight line like this, and then we're going to encounter BY, which is going to push us up to 0, and we're going to have this closed and shaded in shear diagram. We're going to call this distance D right here, and we're going to call this distance 10 feet minus D, and we're going to use similar triangles to solve for these two distances D. And so we're going to say D over 187.5 pounds equals 10 feet minus D over 112.5 pounds. And doing some rearranging, we can solve for D as 6.25 feet, and we'll get 10 feet minus D is 3.75 feet. Now that we know these two distances, we can easily draw the moment diagram. And you need to remember from your knowledge of statics, the moment diagram is generated by finding the area beneath the shear diagram. So more specifically, the change in moment is comes from the area under the shear diagram. So at the fixed connection at A, we had that moment reaction, and that was going counterclockwise. So that's going to push us down to a negative 375 pound-feet. And then we have this positive area that we're going to calculate as our first change in moment. And that's going to give us a parabolic arc. And we're going to see this parabolic arc come up to a value of 211 pound-feet. And then we're going to have another change in moment, which is this negative area, which is going to parabolically close us down back to 0 here at the 10-foot mark. And we can shade this in, and this gives us our moment diagram. And so that's the summary of this example, using the force method or the redundant method to solve for that redundant reaction BY. And then from there, it's just basic statics principles to solve for the remaining external reactions and then sketch the shear and moment diagrams. If you found this video helpful, please hit like and subscribe.